Всем привет! Hello everyone. So welcome back to another video of Marin Maths. And today I'm going to do the video review for Calculus 112 Common Exam. Alright, it's also known as Calculus 2. So I'm going to go over, I think it's 9 questions. 11 questions actually. Yeah, this test is going to be a little bit longer than the last one. And the version is 2016. So if you go to the NJIT website, at njit.edu, you will find the common exam practices over there, so you can check it out. I'm going to put it on the description so that you can follow up. Alright, so I'm going to start off by looking at number 1. Okay, so for number 1 we have the integral of x times e to the negative 2x dx. Okay, and for this, the most convenient method to use, okay, is definitely integration by parts, right? So let our u equal to x, right? Because if you think about it, if you differentiate u several times, at some point you will have 0. So that's convenient. Our u is x, dv is equal to e negative 2x dx. So that means that integral of u dv is equal to the u times v, right? Minus the integral of v times du. Okay, so let's go ahead and do that. So we're going to multiply, okay, u times v. So we have u. So that's going to be integral e of x times e to the negative 2x dx equals to u, okay, which is x, times v, which is this integrated, right? Integral of e to the negative 2x in this case will be, okay, minus a half e to the negative 2x. All right, so that's going to be our v. So u times v, so this times negative 1/2 e to the negative 2x. And then we're going to subtract the integral of v du, integral of minus 1/2 e to the negative 2x. And then du is, of course, du dx. Okay, now negative times negative becomes positive, right? So this is just that. And all we have to do is integrate 1/2 e to the negative 2x dx. And so our final answer will be something like this. It will be equal to negative x over 2 times e to the negative 2x, right? And then we're going to have minus 1/2 times negative 1/2, which is 1/4 e to the negative 2x. And don't forget your arbitrary constant of integration, okay, plus c. Very nice. So this is question 1. Okay, there is no part B, or it's not split up into several parts. All right, now question 2. All right, for question 2, what we need to do, okay, is we have to integrate, okay, 5x cubed minus 3x squared plus 2x minus 1, all of that divided by x to the 4th plus x to the 2nd power. Yeah, this is x to the 2nd power. All right, and so dx times dx. Now, in order to do this integral, okay, I think the most efficient method, the best and the fastest method here will be to split this fraction, okay, into the sum of partial fractions, right? So we're going to have to use partial fraction decomposition. That's the best method, okay, to use in this case. All right, so clearly what we have to do is split up the denominators. So we have to factor it out. So we're going to have 5x cubed, okay, 5x cubed minus 3x squared plus 2x minus 1, and then all of that divided by x squared times x squared plus 1. Okay, so and then what we want to do, okay, is split this up into the sum of partial fractions. So we're going to set it equal to, okay, some constant a divided by x plus some constant b divided by x squared. And don't forget about your last factor, which is going to be x squared plus 1. So in that case, it will be plus some constant c times x plus some constant d, all of that divided by your squared factor. Okay? So that's how partial fraction decomposition works. And now what we're going to do is we're going to find the common denominator, right, of this fraction. So what we have is, we have 5x cubed, right, minus 3x squared, okay? And then we're going to have plus 2x minus 1. All of that is equal to, okay, Now, if we find the common denominator on both sides, we know that the fractions will, on the bottom, right, the denominator will cancel out, right? So we just have the numerators. Over here, what do we have to multiply to find the least common denominator? Well, we need an x, and we also need x squared plus 1. So we have a times, right, a times, well, let's put ax, right, because we need x, times x squared plus 1. And then we have plus b. What do we need? Do we need an x? No, we already have x squared. We just need x squared plus 1. So it's b times x squared plus 1. And then plus cx plus d. And then we're going to multiply that by whatever we need, which is x squared in this case. Now let me just erase this over here because we have no more space. All right, so that will be multiplied by, okay, x squared. So remember, we want to split this into an integral that goes like this: a over x plus b over x squared plus cx plus d divided by x squared plus 1 dx. Okay, so that's our final goal, and then integrate it afterwards, which is the easiest part, okay, to do. Now, over here are some important things we have to keep in mind, okay? First of all, what we want to do is we want to, okay, find which constants, okay, which constants will be equal to these numbers over here. So we have an x cubed factor, x squared factor, x factor, and we have a constant. So we want to expand this over here and see what happens. We want to factor out all constants and have something like this, okay? Instead of numbers, we're going to have a, b, c, and d. So let's see what we can do here. We have x cubed, right? We have an a multiplied by x cubed. So let's start with x cubed. We have a, right? And then what else? Do we have bx cubed? Well, not really. We don't have bx cubed. Do we have cx cubed? Yeah, we do have a cx cubed. So we factor out a plus c. All of that multiplied by x cubed. Okay? Now let's find the x squared factors, right? So we have ax times 1. No, that doesn't work out, right? bx squared, that's one x squared factor, that's b. And then over here we have dx squared. So b plus d multiplied by x squared. Now let's find our our x factors. So we have 1ax, right? So 1a plus, we have, I think that's about it. Yeah, there's no other x factors over here, right? If you try to factor that out. So that's just going to be a times x. And finally, let's find our constant factors, okay? In which case will be just b. b times 1 is b. And there you go. Now, you can compare this equation over here, okay? 5x cubed minus 3x squared plus 2x minus 1, right? That's equal to this expression over here. So, right over here we have 5, okay? Which means that, okay, this expression over here, this factor, a plus c, will be equal to 5. So we can say that a plus c will be equal to 5. Okay, what else can we say? We can say b plus d, okay? b plus d equals to negative 3. And a equals to 2. And so b equals to negative 1. We already found two of them by themselves. Now we have to take advantage of this information over here in order to find our answers to D and C, okay? So over here we know A is 2, so that means that C is 3. And over here B is negative 1, so D is negative 4. We already found all constants. How easy was that, right? Using partial fraction decomposition. And remember, in the common exam, you're not going to have like a really crazy integral like the ones you have on your homework. So don't worry about it. Just try to like see which method fits best in the situation, which in this case is partial fraction decomposition. Now, let's substitute our constants into the new integral, okay, split up as partial fractions, right? So the sum of partial fractions will be equal to, okay, the integral of this will be the integral of 2 over x plus, okay, b was negative 1, right, negative 1 divided by x squared, and then we have plus c, in which case is 3x minus 4, right, divided by x squared plus 1 dx. Very nice. Now this is so easy to integrate over here, but first of all, let's try to split up the last term a little bit more, okay, so what do we have in here? We have two terms in the numerator and one in the denominator, right? Well, essentially one factor, right? So what we could do is we could, okay, distribute this. So we have, instead of this, we have 3x over x squared plus 1, and then we have minus 4 over x squared plus 1 dx. Now that's way easier to integrate now. So the answer will be something like this, okay? It will be equal to 2, okay, times ln of absolute value of x, okay, minus the integral of 1 over x squared, which is minus 1 over x, so that will be plus 1 over x. And over here, we have to let u equals to x squared plus 1, okay, u equals x squared plus 1, so the u is dx, okay, and then we have 2 dx, right? Because this is 2x dx, so we have 2x dx, but we divide this by 2. And we already have a dx over here, x dx, right? So we're going to have plus 3 halves, okay, integral of 1 over u, which is just ln, absolute value of u, which in this case is x squared plus 1, okay, minus 4 times integral of 1 over x squared plus 1, which is just arctangent. Or you could also say that this is plus 4, okay, cotangent, or no, not cotangent, but arc, okay, cotangent, inverse. No, I can't say that. It's either arcotangent or cotangent inverse. But I like arcotangent, but it's more fancy, okay? So, and then of x plus c. There you go. That's your answer, ladies and gentlemen. All right? No negatives, so that's why I got rid of the negative. I mean, you could still say it's minus 4 arctangent or tangent inverse, but that's equivalent. That's all right. Okay, for question 3, we're asked to take the integral of 1 over 4x squared plus 9, all of that to the power of 2 dx, right? Now, in this case, I think the most convenient method is to take, okay, to make a trigonometric substitution. In this case, as you can see, you have something squared plus something else, right? And that sounds like, okay, tangent squared theta plus 1 equals to secant squared of theta, right? So how about we make a substitution in such a way that we can use this identity, right? So how about, for example, we let x equals to, suppose we want to get rid of the 4, so we want something that's the square root of 4, so 1/2, right? Because when we square it, we get rid of 4, and then multiply it by 3, because in that case, we're going to have 9, and we can factor it out of this expression and use the identity, and then of course multiply it by tangent of theta. So what happens when you square it? Well, x squared will be equal to 9 over 4 tangent of squared theta. As you can see, the 1/4 will cancel out, and we can factor out the 9. Excuse me. Now, let's find the x. The x is just going to be 3/2 secant squared theta, d theta. So that means that the integral of 1 over 4x squared plus 9 squared dx is just equal to, okay, integral of dx, which will be 3/2 secant squared theta d theta, divided by, okay, in this case we have 4, okay, times x squared, which is 9 over 4 tangent squared theta, and look at that, the 4 cancels out, and then plus 9, okay, all of that squared. Over here we can factor out 9, right? So eventually we're going to have something like this. We're going to have 3/2 integral of secant squared theta d theta, right? And then we're going to divide that by, okay, factor out 9 squared, right? Don't forget about the square, that will be 81. So we can bring it outside of the integral, so it's 81 times 2, okay, over here. But you know that 81 divided by 3 is 27, so we can cancel that out. So it's 27 times 2, which is 54, right? So we have tangent, okay, tangent squared theta plus 1 squared. That's what we have left. And so if we use the identity, okay, this thing over here will just be secant squared theta. And if we square that, we're going to have something like this, 1 over 54, right? Integral of, okay, we have secant squared theta d theta divided by, okay, secant squared squared, so that's secant to the 4th power of theta. And look at that, we cancel out 2 powers and we're left with 1 over secant squared theta, which is just cosine of theta. So we have something like this. This is equal to 1 over 54 integral of cosine squared theta d theta, in which case will be equal to 1 over 54 integral of 1 plus cosine 2 theta, all of that divided by 2, d theta. Okay, we bring 1/2 outside if you want, or you could just straight up integrate this. So we have 1 over 54, okay, times integral of 1/2 d, times d theta, which will just be 1/2 of theta, and then we have plus integral of cosine 2 theta over 2, which will be 1/4, okay, sine 2 theta, all right, and then all of that plus c. And of course, don't forget to substitute back into theta. We know that theta, okay, theta in this case, or tangent theta, will be something like this. If we solve for tangent theta, we have tangent of theta equals to, okay, 2x divided by 3. So 2 times x over 3. And so if we use a right triangle, we have, okay, something like this. We have theta over here. And so tangent of theta, the definition will be opposite over adjacent. So we have 2x on the opposite side, okay, and then we have 3 on the adjacent side. So that means that in accordance to the Pythagorean theorem, we have that the hypotenuse is equal to 4x squared plus 9. And that is very familiar, right? That looks like the bottom term over here. It's just square rooted. And so we can make our substitutions over here, given that we have theta, okay? Well, theta in this case will be our tangent of that, right? So theta is just arctangent of 2x over 3. So let's go and do the substitutions over here. So the integral of that will be equal to 1 over 54, okay, times 1/2 arctangent, right, of 2x over 3. And then we're going to have, okay, we're going to have right over here plus 1/4 sine 2 theta. Okay, sine 2 theta is basically, okay, if we have 2 sine theta, right, times cosine of theta, that's basically 2, I'm sorry, not 2, but sine of 2 theta. Okay, so we substitute sine 2 theta, we have 2 sine theta cosine theta, so we have times 2, and then sine theta, according to the triangle that we made over here, is opposite over hypotenuse. So it will just be 2x over the square root of 4x squared plus 9, and then multiplied by cosine theta. Okay, so cosine theta is adjacent over hypotenuse, so that's going to be 3 over square root of 4x squared plus 9. Okay, and don't forget, okay, plus c. So close this parenthesis and plus c. Now let me erase the top so I could make space for the answer. So over here we have something like this. So if we simplify, we have that the integral of 1 over 4x squared plus 9, all of that squared dx, will be equal to, okay, 1 over 54, 1/2 arctangent of 2x over 3. And then we have 2 over 4 is just 1/2, so it's plus 1/2, right? And then we have 3 times 2 is 6. So it's actually 6 halves, which is just 3 times x divided by this times this, okay? If you combine this together, you're going to have, okay, the same, okay, factor, just to the first power. So 3x over 4x squared plus 9, and then we have all of this plus c. Don't forget your c. So this will be the integral using trigonometric substitution, okay? For question 4, we have the integral of tangent cube x over 2 times secant cube of x over 2. Now, first of all, the one thing we want to do is we want to have, okay, just one variable multiplied by 1 in the inside. So let's just make a substitution. Let u equals to x over 2, which means that du times 2 is equal to dx. Okay, we can substitute that in there. So this is essentially equal to 2 times the integral of tangent cube of u times secant cube of u, du. Okay, now right over here we have a special case of trigonometric integration. So we know that when we have tangent to the nth power times secant to the nth power, well, and then given that they are both odd powers, one thing we can do, and it's very special, is we can split off, okay, a factor of tangent secant, right? Tangent u, secant u. So let's try that out and see what happens. So we have that this is equal to 2 times the integral of tangent squared of u times secant squared of u times secant of u tangent of u, right? du. And why are we doing this? Well, you will see why. What happens when you, for example, take the derivative of secant of u? You get secant tangent, right? Excuse me. So what you're going to do is use trigonometric identities to make sure that all of this in this side, right, will be, okay, in terms of secant of u. Doesn't matter which power, right? As long as you can convert this into secant. So how about we make, okay, another substitution? In this case, let's introduce the substitution. Let alpha equals to, okay, secant of u. So that means that d alpha equals to secant u tangent of u du. So we continue, and we're going to get something like this: 2 times integral of, over here we know that tangent squared u plus 1 equals secant squared u. So we can, okay, subtract 1 on both sides, and we're going to get something like this. We're going to get alpha squared minus 1, okay, all of that multiplied by, okay, alpha squared, times d alpha, right? Because d alpha is secant u tangent u du. And this is extremely convenient, as you can see. So we have this integral is equal to 2 times integral of alpha to the 4th power, right? Minus alpha squared d alpha. So final answer should be equal to, okay, 2 times alpha to the power of 5 over 5 minus alpha cubed over 3 plus c, and then we make back our substitutions. We know alpha is equal to secant of u, and u is x over 2. So that's equal to 2, okay, bracket, times secant of x over 2, okay, to the 5th power divided by 5 minus secant to the power of 3 of x over 2 divided by 3. Don't forget plus c. So that will be the result for this integral. Okay, so for question 5, we have the integral of cosine of pi x times e to the x dx. And this integral is a special one because it will repeat itself, okay? It's going to be very a repeating pattern, right? So we're going to find, okay, the second factor after we do the integration by parts, which is the most convenient method in this case. Excuse me. So let u equal to, in this case we could say e to the x, for example. It doesn't matter, so we could say e to the x, and our dv to be equal to, okay, cosine of pi x dx, right? So according to integration by parts, we have that the integral of u dv equals to uv minus integral of v du, right? So let's find out what du is. Du in this case is just the same as ex to the ex dx, and then v equals to 1 over pi sine of pi x. Okay, so let's find what the integral of cosine pi x ex dx is. In this case, that's going to be equal to uv, which will be, okay, 1 over pi sine of pi x, right? Multiplied by e to the x minus the integral of v du, which is 1 over pi sine of pi x, and then multiplied by du, right? Integral of v du, which in this case is ex dx. And we have to do another, okay, integration by parts. In this case, let's let u equal to ex again, and dv to be 1 over pi sine of pi x dx. So that du is the same as e to the x dx, and v to be negative 1 over pi squared cosine of pi x dx. Okay. So we can make the the substitution over here. So we know that this is going to be equivalent as 1 over pi sine pi x, right, times e to the x, right, and then we're going to subtract the integral of 1 over pi sine x sine pi x e dx, which in this case will be uv, right? So minus 1 over pi squared cosine of pi x, right, multiplied by u, which will be e to the x. And then we're going to subtract the integral of v du. So v is this, du is this. So we're going to have minus 1 over pi squared cosine pi x, and then du is ex dx. Nice. We've reached the point where we have the integral of this equals to all of this. And if you notice, okay, over here, we have the integral of 1 over pi squared times cosine x, cosine pi x times e to the x dx, which is essentially the same as this with a different factor. So what we want to do is we want to take those factors together and then factor it out, right? That's naturally what we would do. So let's distribute the signs over here. So we have that the integral of cosine pi x times e to the x dx equals to 1 over pi, right? 1 over pi sine of pi x times e to the x. Negative times negative is positive. So it'll be plus 1 over pi squared cosine of pi x times ex. And then we have negative times negative is positive. So plus integral of 1 over pi cosine, pi squared, right? Cosine of pi x e to the x dx. And look at that. Okay. So what we got here now? Oh, and right over here we have this is negative times negative is positive, and times negative is negative again. So this over here in the inside is negative actually. So look at this. We got the integral of cosine pi x ex dx equals to something 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 plus, or minus 1 over pi squared cosine of pi x ex dx. So what do we add this on both sides and factor out 1 over pi squared plus 1, right? So if we factor out 1, okay, over pi squared plus 1 times integral of cosine of pi x times e to the x dx, okay, that's equal to that, and then we know that the final answer will be cosine integral of cosine pi x times e to the x dx will be equal to this over here divided by our factor, 1 over pi squared plus 1. And let's see what we could do with this. Can we find the common denominator? Well, let's see, 1 plus pi squared, right? All of that divided by pi squared. So we just multiply by the reciprocal on both sides. And that will be something like this. That will be pi squared, right? Over pi. And then we're going to have sine of x, right? Sine of pi of x times e to the x plus pi squared over pi squared. Look at that, that cancels out. Cosine of pi x times e to the x, right? And then all of this will be divided by, okay, the factor 1 plus pi squared. And don't forget plus c. So your final answer should look like, okay, pi times sine of pi x, right? Because we cancel out 1 pi over here. And then plus cosine of pi x, right, to the times e to the x. All of that divided by 1 plus pi squared plus c. That would be the answer. Okay, so for question 6, we have the following. Okay, so does the sequent, okay, 1 minus 3n divided by 1 plus 2n converge or diverge? If it converges, to what value do the terms converge? Okay, this question is actually very easy. We can approach this using either, okay, L'Hopital rule, which is awesome, okay, it just gets rid of everything. It destroys every limit, okay? Or we could, okay, use the, the sequence rules, okay, the limit rules for sequences. But in this case, let's try both, okay? So let's see if we take the limit of this as it goes to infinity. You know, at infinity, everything, okay, converges or diverges. So let's see. Let's take the limit of the sequence, okay, as n goes to infinity. Okay, so 1 minus 3n over 1 plus 2n. And if we use L'Hopital's, okay, L'Hopital's rule, then we can say that this is basically equal to the limit, okay, as n goes to infinity of the derivative of the top part, which will be minus 3, right? Divided by the limit as n goes to infinity of the derivative of the bottom, which will be 2. So if we take the limit of negative 3 halves as it goes to infinity, that will just be negative 3 halves. And that will be the value to which the sequence will converge, right? But suppose you want to use the, the difference rules, right? The difference rules for sequences, the limit rules. I mean, one thing we could do is, we could do something like this. Look, limit as it goes to infinity, excuse me, of 1 minus 3n divided by 1 plus 2n. Okay, one thing we could do is divide top and bottom by n, right? So if we divide the top and bottom by n, we get something like this. The limit as n goes to infinity of 1 over n minus 3 divided by 1 over n plus 2. Okay? And if we take the limit of this as it goes to infinity, you know that this over here dies, it goes to 0. And this over here dies as well, so it goes to 0. And we have negative 3 halves. So that's one way or another to find, okay, the convergence of this sequence. And we can say, of course, it converges, okay? So for question 7, we have to integrate x cubed dx divided by the square root of 1 minus x squared. Okay, in this case, well, I mean, the most convenient method to use will be trigonometric substitution, given that we have a term, okay, of 1 over the square root of 1 minus x squared. So the most effective substitution that we could do is let x equal to sine theta, in which case the ex will be cosine of theta d theta. So we can make our substitutions, and this is equivalent to the integral of x cubed, which will be sine cubed theta, dx which will be cosine of theta d theta. Okay, all of that divided by 1, the square root of 1 minus sine squared theta. All right, and then look at that. This over here will be equal to cosine squared theta. So cosine squared theta to the power of 1/2 is cosine theta, and look at that. Cosine theta and cosine theta cancels out. So we have the integral of sine cubed theta d theta. All right. So what can we do here now? All right. So we have the integral of sine cubed theta d theta. One thing we could do is, well, split off, a factor of sine theta and see what happens, right? Because what happens when we have even powers of a trigonometric function? Well, we can use, a trigonometric identity, right? So we can use a trig identity. Excuse me. So that's equivalent to the integral of sine squared theta times sine of theta d theta. What happens if we let this, equal to 1 minus cosine squared theta, right? We're using the identity times sine theta d theta. We can let u, right? We can let u equals to cosine theta, in which case du will be equal to negative sine theta d theta. All right. So this will be equal to the integral of 1 minus u squared times sine theta d theta, which in this case will be negative du. So negative du. All right, so this is the integral of u squared minus 1 du, which will be u cubed over 3 minus u plus c. Now we can make our substitutions. We know u is cosine theta, and we know that sine theta equals x, so we can make a triangle over here. This is theta, sine theta is x over 1, so this is the square root of 1 minus x squared. So we can say that this is equal to u cubed, which is cosine cubed theta over 3 minus cosine theta plus c. Okay, and in this case we know that that will be equal to cosine theta, which will be adjacent over hypotenuse, right? So that will be the square root of 1 minus x squared, and so the answer will be the square root of 1 minus x squared to the power of 3. All of that divided by 3, right? And then minus the square root of 1 minus x squared plus c. Okay, so that would be the answer for this question, number 7. Okay, so we have 2 questions over here, which are pretty short, relatively short. So we have 8, integral of x cubed, the cube root of 4 minus x to the 4th power. Okay, and well, in this case, you can see that if we make a substitution, right, that'll be pretty straightforward. So let's let u equals to 4 minus x to the 4th power, which in this case will be, okay, du will be minus 4x cubed dx. So if we divide by minus 4 on both sides, we have du over negative 4 equals to x cubed dx. So we can substitute this into the integral. So we have the integral of negative 1/4 times the integral of, okay, the cube root of u du, right? And the cube root of u du, okay, the integral of that will be minus 1/4 times, right, times 1/3 plus 1, which will be 4/3, right? So 4/3, and then, okay, multiplied by the reciprocal, so times 3/4 plus c, okay? So right over here, we can substitute, and then let's see what happens. So 4 times 4 is 16, so we have that this is minus 3 over 16 times u, which will be 4 minus x to the 4th power to the power of 4/3, right, plus c. This will be the answer to question 8. Now let's look at question 9. Integral of 1 over 1 plus x squared dx from 1 to infinity. Okay, this is the first indefinite integral. I mean, the first definite integral in this practice exam, and it's an improper integral. So here's how we're going to treat this integral. Okay, so first of all, we have to rewrite this as, okay, the limit of the integral from 1 to b as b approaches infinity, right, of 1 over 1 plus x squared dx. Now we can integrate this and then, evaluate our limits of integration at 1 and b. So we have that this is equal to the limit as b approaches infinity of the integral of 1 plus, okay, 1 over 1 plus x squared, which we know is tangent inverse, right? So that'll be arctangent of x from 1 to b. And that'll be equal to the limit as b approaches infinity of, okay, arctangent of b minus arctangent of 1. Okay, now we know that the limit of arctangent of b as b approaches infinity will be indeed pi over 2. So that'll be approaching pi over 2. And then the arctangent of 1 will just be pi over 4, so minus pi over 4. And that'll be equal to positive pi over 4. So this integral converges to pi over 4. Okay, so the integral converges. Okay, so for question 10, we have the integral of ln of x dx from 0 to 1. So again, this is an improper integral because ln of x is not defined at x equals 0, right? So that means that, okay, we will have to set this equal to the limit of the integral from a to 1 of ln of x dx, okay, from, okay, as a, okay, approaches 0, but it has to approach 0 from the positive side, from the right, 0 plus, right? And so that will be equal to, okay, the limit as a approaches 0 from the right, okay, of the integral of ln of x dx. And we have to use integration by parts. So in this case, let's integrate this indefinitely. Integral of ln of x dx, okay? So if we let u equal to ln of x, then dv will be dx. So according to integration by parts, the integral of u dv will be equal to uv minus integral of v du. Okay, so we have that this is equal to uv, right? That will be integral of ln of x dx equals to uv, which will be ln of x times integral of dx, which is x. That's v. minus the integral of x du. du is 1 over x dx. And look at that, this cancels out. So we know that the integral of ln of x, right, dx will be equal to x ln x minus x plus c, the indefinite integral, right? But we're doing an indefinite improper integral over here, so this will be the limit as a approaches 0 from the right of x ln x, right, minus x from a to 1, okay? And so as the limit approaches, as a approaches 0 from the right. So this will be equal to the limit as a approaches 0 from the right of, okay, 1 times ln of 1, and that's going to be equal to 0, minus 1, okay, and then we're going to subtract a ln of a minus a. Okay, so what's special about this over here, the limit? So the limit as a approaches 0 from the right, if you think about this, okay, that will be ln of something really small, okay, which will end up being infinite, right? It will end up being very, very large. I mean, very close to infinity, to negative infinity. But then it's multiplied by a, which is 0, and anything multiplied by 0, well, it's just 0. So that dies out, and well, a, okay, is 0, so that just is 0. So we have that this integral, okay, the integral from 0 to 1 of ln of x dx is equal to negative 1. So that tells us that this converges. Okay, so that's it for question 10. Moving on to the last question. Okay, so for question 11, the last question, we're going to use the trapezoidal rule, okay, which is used to approximate the integral of f of x dx from a to b, and we're going to use Tn is equal to delta x over 2, okay, times that formula over here, where delta x is b minus a over n, and the y sub i's are evaluated at the partition points. So for part A, we're going to use the trapezoidal rule to estimate the area under the curve, y equals mx, okay, over a and b, right? So the interval, the closed interval from a to b, with n equals 2 partitions, okay? So we can go ahead by, okay, we're gonna start by drawing our 2 partitions, right? So we have A over here in the beginning, and in the end we have B. We have to have 2 partitions. So what goes in the middle? Well, we have to find what's delta x. Delta x is b minus a over n, and in this case n is 2, right? So b minus a over n is in fact, okay, delta x. So we add delta x to a to find what is our next point. So a plus b minus a, okay, over 2 will just be, okay, it will just be b plus a over 2, okay, because 1 minus 1/2 is 1/2, so we just have b plus a over 2. So b plus a over 2 will be our second point. So we have now 2 partitions, 1 and 2. Now, what we're going to use now is the trapezoidal rule, so Tn will be equal to delta x, which in this case is b minus a over 2, right, over 2, and then all of that multiplied by y0. So we only have y0, y1, and y2, okay, y final. So in this case it will be y0 will just be a, right? So it will just be a times m. So a times m, because this is the function we're trying to integrate. So a times m plus 2 times y1, which will be, okay, m times y1 will be b plus a over 2, and then plus y final, which will be, okay, m times b. Okay, once we simplify all this, look at this. 2 cancels out. 2 over 2 is 1/4, so that will be something like this. We can factor out an m as well, so t will be equal to b minus a over 4 multiplied by m, and then times a plus b plus a plus b will then be 2 times a plus b. And look at that, 2 over 4 is 1/2, So we have that this is equal to b minus a times b plus a multiplied by m over 2. So this will be our trapezoidal approximation, okay, given two partitions. And if you really think about it, we're approximating the area under the curve of a line using trapezoids, which essentially is the actual area, right? So let's see what happens when we take the integral, okay, directly for part B. So let's take the integral from a to b, okay, of m of x, mx, m times x dx, right? So this will be the integral, okay? So this is essentially mx squared over 2 from a to b, right? And if we just substitute, we're going to have something like this. M over 2 times b squared minus a squared. And since you know that this is two squares, the difference of two squares, that would just be equal to m over 2 times b minus a times b plus a. And that's, okay, the answer for the integral. And as you can see, that's essentially the same, okay, as the trapezoidal approximation, which means that there is absolutely no error. So if you go to part C says that the error formula for trapezoidal rule, okay, the error formula, I'm going to write it down over here. So the error formula for the trapezoidal rule is going to be like this, okay, E of t, absolute value, is less than or equal to the second derivative, okay, at some point c multiplied by b minus a to the third power divided by 12n squared. So this is the formula for the error, where c is chosen on the interval from a to b, on the closed interval, right? And we're going to maximize the second derivative, the absolute value of the second derivative at this point. Use this, okay, to explain the difference between your answers in part A and part B. Well, we saw that the difference in answering part A and B was absolutely 0. Okay, they were exactly the same. And that is because the second derivative, okay, the second derivative, d over d x of d over dx, right, of mx, okay, will just be equal to 0. So that means that this will be equal to 0, this whole expression. The error, okay, the error for the trapezoidal rule will just be equal to 0, okay, which means that the answers will be the same, okay. The actual integral is equal to the approximation, which is a pretty good approximation, right? Is 0% error, right? So that is why there's no difference. No difference. Okay, I think that concludes this common exam review for Calculus 112, okay, number 2, okay, the common exam number 2. And that's coming up next week. So I wish you the best and good luck. I hope you found this video useful. Thanks for watching, okay, and share it with your friends, and I will see you next time. Have a good night.